This tutorial is about using graphical method to find roots of equations in single variable. This is linked to the problem, first problem in the lab manual, where we are trying to find out the critical depth of open channel flow where the cross section is trapezoidal. And we derive this equation. This is an equation in a single variable, and it's a function that is equal to 0. So we are to find out where the y, at what y values this function becomes 0. This is a 6-degree polynomial, and one of the exercises requires you to check that this is a 6-degree polynomial. And so the first part is finding what this graph looks like. What is the shape of this function at different values of y? And of course, eventually you want to find those locations where the function crosses y-axis. So in this graphical method, we will be using arrays and plot a function f6, the 6th order polynomial that we have in this problem. So in order to do that, first of all, we will create the function. I'm calling it f6, but you can call it whatever you want to call it. And then I have coded this function takes the input value y and then finds the corresponding value of this function fy and returns it. And then we will use this one in our script where we will call this function. So I will write the script from scratch, and let's call this script to run f6, to plot f6. Okay. And then let's save this as plot f6. Okay. Here we will create two arrays. One is called y, and then we want to plot this function at 1, 2, 3, 4, and 5. These 5 points. And then we want to find fy, which will be exactly the same size, but will have the values in it, which we need to calculate. But as of now, we don't have those values. So what we can do is we can create a for loop for, say, n equal to 1 to 5. I know this is 5 length, and I always like to put the end first. And then I can say fy n is equal to f6 y n. So anytime I want to access the value of the y at a certain index, then n is the index of that. You can think of n as the subscript of y. So for example, if I copy paste this line here, then y at index 5 has a value of 5. Okay, whatever is the value, so it could be something else. So anyways, now we can create a new matrix which will have the value of the function calculated at that y point as the corresponding values. So if I run this loop, let's clear our workspace and run this script. So we just run this script. As you can see, it has n, y, and fy created. If I look at y, I have my 5 points at which I want to calculate the value of the function. And then if I look at fy, I have the values of that function. And you can very clearly see that before 1, it has a positive value, and then at 2, it becomes a negative value. So clearly the root lies somewhere between here, and then it stays negative. But maybe it may not have been, a lot of values here. So in that case, you can always create a plot of this function. And you can use plot command, which I taught you in the last lab, and provide the x-axis values and y-axis values. And this will plot it. And now you can see that at some point it crosses the 0. Of course, we don't know exactly when. We will have to create more y values to do that. And that's very easily doable. Let's say we wanted to increase the density of points along the y-axis. I can actually change this array and using a different command called linear space. So make sure you type help lin space and look at this little tutorial that describes what linear spaced vector is. So we create a linear space from 1 to 5 with 100 values in it, and that's typical usage. You can describe it to have as many points as you want, but it will divide the interval 1 to 5 into equal intervals, equal 100 intervals. And of course here I have to now go from 1 to 100 to find the value of the function at each one of those y points, and then I can run it, and you can see that the function becomes much more smooth because I am now finding the value of the function at each y. Now you can also view this. If you type y, you will see it has 100 values, and similarly if you type fy, you will see it has also 100 values. So this is how you can create a graph of the function, and now we can analyze this graph to find out where is the root of this function. Now often it's very difficult to see the values, and a command called grid on will place a grid on this, and now we can more clearly see that 0 happens around 1.5. So if I created a bracket somewhere between 1 and 2, I should be able to home in onto the root through a bracketing method. Or if I started an initial value somewhere close to this point, I can quickly find an accurate value of the root for this function. Now grid can be turned off as well by saying grid off. So you can use this function as needed. So this concludes the graphical method of finding the root of a function in single variable.